All right, we're quiet, so that means we get started, I guess. All right, so I just wanted to mention some of the, I guess, tasks that you guys need to do this weekend or in the coming days. So on my part, lecture part, please remember to do the syllabus gatekeeper quiz, because then that will unlock chapter 2 for you, and we will start chapter 2 next week. Remember our rule for online homework. Those chapter homework sets are due as soon as we finish the chapter in class. We are not going to finish chapter 1 today. So is there a homework assignment due this weekend? No, there's not. I think if you look at the calendar, it's due next week, but still, a due date doesn't mean a due date. You can still look at the questions, do what problems you can. That will save yourself so you don't have to do 3 hours of homework in one sitting, on a Sunday, all right? Okay, so there's that. It's very important you do the academic misconduct quiz. Very, very important. And I think it's due on Sunday because this is our participation roster. As you know, I cannot take attendance in this classroom. It is just not feasible. There's too many of you. So that academic misconduct quiz is our participation roster, meaning if you do not take it by Sunday, you will be dropped from this class for non-participation. All right, so it's very, very important you take it. All right, and so it's on your to-do list, all right, academic misconduct quiz. What else? I think there's some lab things that are due. Is that introduction to smart worksheets due this Sunday? Is it due? It is due this Sunday? Okay, it is due. And I believe if you click on the Achieve website, that assignment, it kind of gets buried at the bottom, all right? So you have to kind of go looking for it, but it is in fact due this Sunday, all right? So according to the Carmen thing here. So don't get confused. Just, do it now rather than later. And then some other things here, okay? Lab safety, things like that. So work through those start of term tasks on our Carmen page. Any questions about this? Okay. All right. I did want to announce, I mentioned before that there are teaching assistant office hours in Celeste 170. It's a room very close by to where you bought the lab coat. It's kind of just like, you turn right to get to the lab coat, but to get to the TA help room, you go to the left. So I want to show you where to find information about the teaching assistant office hours. So once you're on the home page of our Carmen site, if you kind of scroll down, there's this page right here where it says Chem 1210 resources, I think, on this page. This is where you can find the email addresses of your teaching assistants, other information, the lab supervisor email, things like that. But I want you to see this link right here, your Gen Chem office hours. So if you open this link in Chrome, I think is the best. This is the list of all of the office hours of the Gen Chem staff here. But realistically, there are thousands of 1210 students, this term. You can drop in any time that the TA help room is open to get help. So the very important thing here is you do not have to just go to your teaching assistant. You can go to any 1210 teaching assistant to help you. We're all learning the same stuff. All right, so this is the list of, the certain TAs. Maybe you'll find out like, oh, I really like the way this TA explains this concept. So you'll just go to that TA if you want to. And remember, this is drop in. You can go in anytime with any questions you have. So here are the different people that are staffed in the room. But the important thing to see here is that Monday through Friday, 9 a.m. to 4 p.m., there's always a fleet of people there to help you. All right. So that's like Monday through Friday, basically daytime hours. But there is also evening hours that is available via Zoom. So if you go onto this page, you can see the links here. So these names are hyperlinks. So if you want evening help hours, it's through Zoom. So you just click on the name to go to the appropriate Zoom room at the appropriate time for that TA to help you. They should be staffed within there. So those are evening hours, Monday through Friday. And if that isn't enough for you, there are also weekend hours, all right, to help you. So, Sunday night, when you are struggling with a lab report due in a couple days, there are evening folks here to help you as well. So, do we know where to find this? There's plenty of folks here to help you, not just me, because remember, if you ask me a question about lab, what am I going to do? I'm going to send you to the lab supervisor, because things change all the time. These people are much, much, much more helpful at lab stuff than me. But there's also, for recitation or concept things, they can help you here as well. So I wanted to show you that document here. You can find it on the home page right here under this page. They just posted this like a couple days ago. All right, and so those drop-in hours, it's free. It's literally free, all right? You don't have to pay for a tutor. You don't have to. There's literally like dozens and dozens of people here to help you. All right, any questions? Okay, so let's go back to where we left off, chapter 1. Right, where we were talking about, classification of matter, how we, categorize different substances, and we have the idea that we have pure substances and mixtures. Oftentimes we want to study pure substances in lab because, if something's pure, we know the observations we are making is related to that certain substance. So let's look at the details that differentiate pure substance and mixtures. So my tip here for distinguishing pure substances and mixtures is that a pure substance, stupid pen, all right, first, it's matter when you observe it, it is uniform in properties. But really, the way I distinguish, a pure substance is if you can write one chemical formula or one symbol to represent that sample, then that is a pure substance. So our example we did before, hydrogen gas, H2, that is one symbol. It's one symbol, so we call that a pure substance because we're just writing one formula to represent it. Water, we can represent as H2O, also a pure substance. It just so happens that hydrogen atoms and oxygen atoms are involved in that substance, in that compound, but it's still a pure substance because it's just one formula. Versus something like a mixture, contains two or more substances that are not chemically combined. So my trick is if you write two or more chemical formulas to represent that sample, then it would be a mixture. So let me give you an example. Salt water. Okay, let's think about salt water. Salt water. Salt water contains what? Salt and water. Very good. All right, does anyone know the chemical formula for table salt? NaCl. If you didn't know that, that's fine. That's just like the common word for, we call NaCl, the common term is table salt. So it's made of NaCl. Is there a chemical formula to represent water? H2O. So how many formulas did I use to represent this whole sample, salt water? Two different ones. So see how it's a mixture. I can point to two different things that are present, right? So that would be an example of a mixture. And we'll go into a little bit more detail here within mixtures. There's actually two types of mixtures, homogeneous and heterogeneous. Homogeneous mixtures and pure substances oftentimes are confused because when we talk about a pure substance, we say that it is uniform in properties. But let's think about salt water. Salt water, you just imagine in your mind a beaker of salt water on the table. Does it look uniform in appearance? Yeah, salt water looks exactly like pure water, doesn't it? So homogeneous solutions, homogeneous mixtures also have uniform properties, but the difference lies at what is present in your mixture, the components that make up your mixture. Salt water contains two different pure substances, so that's why we call it a mixture within there. But more specifically, when we think about mixtures, the reason we use two different chemical formulas to represent what's present these aren't combined. They're not in one chemical formula, meaning that they're not chemically combined. We can actually use physical means, techniques to separate those two components away from one another. So this is the big difference between mixtures and pure substances. We can separate the salt and the water in salt water, but if we were thinking about the pure substance, just water, right, that is a pure substance. If we wanted to simplify this further, like separate the hydrogen atoms from the oxygen atoms, we would actually need to do chemical reactions to do that. So that's the big difference. All right, so let's go into more detail about pure substances. So something that we can represent with a chemical formula or a symbol. So there's two different kinds, elements and compounds. So the big difference here, elements, these are our guys on the periodic table here. So if the symbol you're using to represent your sample is just one symbol on the periodic table, then that's an element. A substance is a compound if more than one element is present. So our example, we made water yesterday, or on Tuesday, remember, we took H2, we took O2, and we made H2O. H2 gas is an element because hydrogen is an element on the periodic table. Oxygen, also an element because oxygen is on the periodic table. The only difference here is that there's, twos. So we're just saying that there's two atoms bonded together to make that hydrogen and oxygen molecule. What is different here with water, H2O, there's two elements present bonded together. We know they're bonded because they're written together. So this would be an example of a compound because elements, two different elements are present. So a little bit of clarification of terminology here. Hydrogen, this is an element. Oxygen is an element, but they're molecules because two things are bonded together. Neon or helium, those two substances, how they exist on Earth. Are these elements, are these pure substances, helium and neon? Yeah, they are. They're symbols on the periodic table. But what makes them a little bit different than our hydrogen and oxygen examples here is that these are atoms. Because we write them without any subscripts. They exist as atoms. You may be asking, well, why? Their most stable state, how we observe them in nature, especially our noble gases here, it just exists as atoms. So the idea here, these pure substances, elements, they just come from the periodic table. The other type of pure substance is a compound, something like water, where we have two elements bonded together. All compounds are molecules, for the most part. Because what we said with neon or helium, those substances, those elements can exist as atoms, just singular, but once we start making chemical bonds, we start to build molecules, all right? We start to build more complex things. So when two or more elements are present in a substance, when they're chemically combined, we call that a compound. So for example, NaCl would be a compound because two different elements are present. Water is a compound because two or more elements are present. And what makes this unique, important here is water, H2O, regardless of the source of where you get water, could be like a million-year-old glacier or just, the tap water right here in the lab. No matter where the source of water is, it will always have the composition of two hydrogens and an oxygen. So that is unique to that specific substance within there. Right, so those are compounds, two different elements in the same molecule. So again, clarification of a little bit of terminology here. I mentioned before when talking about elements, we could have atoms where it's just like one atom, the simplest building block of an element, something like helium or neon. But when we have molecules, we have more atoms bonded together. So the idea here is, okay, we can identify a substance as an element or a compound, or an atom or a molecule, depending on how many things are bonded together. So kind of the confusing thing that students encounter is that the elements on the periodic table, some of those elements occur as atoms, Some of them occur as molecules, how we interact with them in everyday life. We can, based upon the chemical formula that's written here, identify an element as an atom or a molecule. This is one of the examples of squares. All squares are rectangles, but not all rectangles are squares type of thing. So I'll show you some examples here. So let's look through these different examples and identify, okay, is this substance an atom or a molecule? And then finally, is it an element or a compound? So CH4 would be, is that an atom or a molecule? Molecule, okay, great. Is CH4 an element or compound? Compound, because more than one element is present. What about helium? Atom or molecule? Atom, element, or compound? What? Element. Okay, very good. All right, the next one, N2. Atom or molecule? Molecule. Why is it a molecule? Two of them bonded together. All right, and then is it an element or a compound? This is an element because just the nitrogen is on the periodic table. So these two is the weird example. Both of these things are elements, right? Helium is something on the periodic table. Nitrogen is something on the periodic table, but one of them exists as an atom. The other one exists as a molecule as we interact with it in our everyday life. So this is really important because if I wanted to kind of communicate, hey, I have a nitrogen atom, which is really actually hard to come by. You don't just walk into that on the street. If I wanted to talk about a nitrogen atom, I would have to say nitrogen atom. So if I say something like nitrogen gas, you should know that that means N2 gas, not N, not just one N, it's N2. All right, so there's a couple of different substances that exist as diatomics on our periodic table. All right, last one here, CO2, atom or molecule? Molecule, element, or compound? Compound. Okay, true or false? All of these substances are pure substances. Ooh. Think about it and then try again. True or false? All four of these substances are pure substances. It is true, because what are the types of pure substances? Elements and compounds. All of these are elements and compounds. So they are pure substances. And remember, what is my trick with a pure substance? If you can write a symbol or formula, it's a pure substance. All right? Okay, very good. All right, so here, more examples of molecules. So a molecule, right? All compounds are molecules, right? Because compounds, we have two or more elements bonded together. A molecule is two or more atoms bonded together. So within that definition, all compounds are molecules, but not all molecules are compounds. So an example would be that diatomic nitrogen that we just looked at. Diatomic nitrogen is a molecule, right? We just said that. But is diatomic nitrogen a compound? No, it's an element because it's just one type of atom bonded together. So within these different pictures, you see most of them are compounds because different colored element, different balls are present here. But oxygen, diatomic oxygen, this is technically a molecule, but not a compound. This oxygen is an element, technically. So this is a space-filling model of different molecules that you see here. Remember, the secret to chemistry is that composition, so the types of atoms that are present in a molecule and its structure, how the atoms are actually bonded together, both influence the properties that we see. So we can read from these structure diagrams what the chemical formula, so the different atoms and the number of atoms that constitute these substances. I think this is a question on your homework within here, but let's see if we can't come up with the molecular formula of aspirin. So we want to tell the reader what elements are present and how many of each atom of each element is present within there. So here you can see our little legend. Hydrogen atoms are white. Oxygen is red, carbon is black. So based upon these number of balls, we can determine the molecular formula of what's there, what is in one molecule of of an aspirin molecule. So let's go one at a time. So let's count how many black balls there are. That will tell me how many carbon atoms there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That sound right? Right? How many hydrogen atoms are there? 7? Are we sure? Are we sure? I'm going to do a different color. 1, 2, 3, 4, 5, 6, 7. Okay, 7. And then oxygen. Oh, 4. Yes, so I will do a different color. So 1, 2, 3, 4. There we go. So that would be the molecular formula of aspirin according to this this space filling diagram. But based upon this picture, we can also see a little bit about the structure of aspirin, all right? How, those carbon atoms are bonded to one another. Does this molecular formula convey anything about the structure of our aspirin molecule? No, it doesn't. All right, it just tells us composition, how many of each atom is present within there. 1, 2, 3, 4, 5, 6. Okay, there we go. All right, so those are some examples of molecules. So let me show you a couple more and kind of reiterate, the secret to chemistry. Both composition and structure are very, very important in the different properties that we study of these of the matter that we study within chemistry. It's both composition and structure. So what I mean by composition is the atoms that are present, okay, in your substance. What I mean by structure is how those atoms are actually bonded together. All right, we already said that a molecular formula doesn't convey how those atoms are bonded to one another. You actually need a structure diagram to show that. So here's an example of 3 different molecules. They all have the same chemical formula, C3, so 3 carbons, 8 hydrogens, and an oxygen. They all have the same formula. If you go in and count like the number of balls and stuff, you'll see that they're the exact same. But if you look and see how those different atoms are bonded together, look at this 1 propanol has an oxygen on the end of the molecule. 2 propanol has that oxygen kind of in the middle of the molecule. Here, this ether molecule has a oxygen atom between 2 carbon atoms. They all have the same formula, the same number of atoms, but they have different structures. They're made of the same Lego pieces, they're just built differently. So they share the same composition, but they have different structures. And the important thing here, and what I want to stress, is that, remember, composition and structure dictate chemical properties. So if we look at one of the properties here that I've showcased is, the boiling point temperatures of these different substances. Way, way, way different. They're all made of the same stuff, but because their structure is different, they have different properties, such as boiling point. All right, so again, composition and structure dictate chemical properties. I think this example is really boring, all right, to showcase my whole secret to chemistry that I always talk about. So I think this one's better, all right? Let's look at these 2 compounds. This is a drug called platinol. The one on the left here, all right? So let's look at these 2 substances. Do they share the same composition? Composition means atoms. They both have a platinum. They both have 2 chlorines. They both have 2 NH3s, right? Right. Same composition. Do you agree with me? They both have the same composition, the same number of atoms, and like type of atoms. You agree with me? Okay. What about their structure? Are they the same? Are they different? They're different. Yeah, so I'll highlight it here. Look at these 2 chlorines on cisplatin. They're on the same side. They're like next to each other. But on the other one, transplatin, see how the chlorines are like 180 degrees away from one another. You see that? Okay. So they have different structure. So they have the same composition, different structure, just like our previous example. But what I think makes this example a lot more interesting is that cisplatin, the one on the left here, this one kills cancer cells. Okay, kills cancer cells. Transplatin does nothing. Does nothing. Just difference of structure, just a difference of how the atoms are bonded together. They have the exact same structure, the same composition, same, platinum, the same things attached to it, but just because of how those chlorines are arranged with one another, one of them literally can kill cancer. It's actually the highest prescribed cancer chemotherapy drug, all right? And the other one does literally nothing in terms of cancer, okay? It has expensive platinum in it. You don't think that's amazing? Right? Again, its composition and structure dictate chemical properties. How the cisplatin kills cancer, those chlorine bonds within the drug structure, when it enters the body, they're replaced by water molecules, all right? And if we think about, if you think about your biology and how DNA, they cross-link, or the DNA strands come together via hydrogen bonds, what happens is what cisplatin comes in, because of how those chlorines are arranged, they're, next to one another, it cross-links with fast replicating RNA and DNA. So something that's fast replicating is something that grows fast, such as a tumor. And that's why cisplatin works very, very well as a chemotherapy drug, right? Only the cis version, the trans version does nothing, because it's not in the right arrangement to interact with DNA. Interesting? Okay, we're all just tired, it's Friday. All right, so there we go. All right, so that's an example. All right, so we talked about pure substances. Now let's talk about mixtures. All right, so my trick with mixtures is if you can point to two different pure substances present, at least two, then it's a mixture, like salt water. Salt water has salt and water. Salt and water both have their own unique chemical formulas. Because I can point to two different pure substances, that is a mixture. All right, so the two types of mixtures that we have are heterogeneous. We don't really talk about heterogeneous mixtures too much. We talk about homogeneous mixtures much more often. So the big difference between these two mixtures are heterogeneous mixtures have non-uniform appearance, meaning is if you have discrete phases that you can point to and separate, that is a heterogeneous mixture. So such as like a pizza. Right? A pizza with like lots of different toppings on it. A pizza is in what phase? Yeah, it's a solid phase. But is everything on a pizza solid? Okay. Oh, like the grease? I guess the grease on a pizza is a liquid too. So see how there's like different phases present on a pizza? But even like the solid toppings on a pizza, they're discrete phases, like the pepperoni and the mushroom or whatever. They're both solids, but they're different phases, like you can separate them from one another. So that is a heterogeneous mixture. We don't work with pizzas and heterogeneous mixtures much in this class. We care more about homogeneous mixtures. These samples have a uniform appearance, all right, down to the molecular level, that you see it very uniformly mixed all the way throughout, all right? But the difference here, because don't pure substances have uniform appearance? And I'm telling you that homogeneous mixtures also have uniform appearance. So it's very difficult to distinguish between a homogeneous mixture and a pure substance. It is. So you have to think about, okay, what is present in that sample in your mixture to determine, the difference between the two. So I mentioned before homogeneous mixtures. A synonym for it is solution. So salt water is a homogeneous mixture. It's also called a solution. Again, they're synonyms with one another. Doesn't always mean liquid. Anything that has different pure substance components in it and is uniform is actually a homogeneous mixture. So another example is something like 14 karat gold. So not pure gold, Pure gold is 24 karat gold. That would be a pure substance. But something like 14 karat gold, that's what I can afford. All right, where they put other metals in there because there are different metals, different elements present. They're all mixed together, but 14 karat gold in your jewelry is still uniform. All right, though different substances are present. That is a homogeneous mixture in the solid phase. Or another example, the air we breathe. The air we breathe. Is the air I'm breathing the same as the air you're breathing? Don't think about it too hard. Yes, it is. I'd hope so. All right. Would you say air is fairly uniform? Yeah. No matter where you go, like air has the same composition. Is air on the periodic table? No. Air is actually composed of a lot of different substances, a lot of different gases. Air contains mostly nitrogen gas, oxygen gas, CO2, etc. So this is a mixture. It has these different gases, but it's uniform. It's uniform in property, but because there are different components present, different pure substances, it is a homogeneous mixture. Or it's homogeneous because it's uniform. It's a mixture because there's different substances present there. So true or false? Air is a solution. True, right? What's the trick that I was trying to get you to fall for? That solution means liquid? It doesn't. Solution just means homogeneous mixture. All right, so there we go. So those are our types of mixtures or types of matter that we study here. So here are some flow charts that might help you, determine or distinguish pure substances from mixtures and the different types. But I think it's just better if we do some examples. I like this one. I like to just know, okay, there's two classes of matter, pure substances and mixtures. Under pure substance, there's elements and compounds. Under mixtures, there's homogeneous and heterogeneous. So let's look at some examples. So first, let's look at a particulate view. I think this one's a little bit easier because we can clearly see whether, there are different components present. Let's match these different pictures with different letters, all right? So this first box would be, what do we see? Let's not even look at the answers. What do we see in that first box? What do we see? Atoms, yeah, the simplest building block. It's just a single ball. So it's an atom. Is atom I guess an atom is one of the options here. So atoms of an element. So let's just kind of check that. Atoms here, so these are atoms. Are they all the same element? Yes. Why do we think they're the same element? The same color, yes. So I guess this first box would be D, atoms of some type of element. All right, what about this next box? Are these atoms? No, they're not atoms. They're not atoms. But are they elements? Yes, they are, because it's still the same color ball here. So which answer would this be? C, yes, molecules of an element. Molecules just meaning, more than one atom or two or more atoms bonded together. All right, the next one. Are these elements? No, because different color balls are present. So each one of these things is a molecule, but technically is a compound because it's a compound because more than one element is present. So this would be what? A, molecules of a compound. And then the last one would just be B, right? Mixture, because we have just different stuff present. So that's what it would look like on the particle level. Which one of these boxes, or if there's more boxes, how many of these boxes are pure substances? How many of them? All of them? 3 of them. Yes, which 3? The first 3. So the first 3 are pure substances. The first 2 are elements. The third one is a compound. Yes, and both of those things are technically pure substances. All right, very good. So let's look at other examples. So picture examples, that was the particle level. Okay, remember, that's the realm of stuff you can't see. These are pictures of things you can see. So something like 14 karat gold or 24 karat gold. 24 karat gold is just our way of saying pure gold. All right, this is pure gold. All right, so 24 karat gold would be considered what? Is it a pure substance or is it a mixture? 24 karat gold. Pure substance. And then let's go a little bit further. Is it an element or is it a compound? Element, yes. So 24 karat gold is an element. There's a song I listened to that said something like pure white gold. Pure white gold. So let's actually answer this next one, and I'll tell you my qualms about that. All right, so 14 karat gold is a mixture, or sorry, I already said it, is a mixture. It's 58% gold. There's zinc, nickel, silver, and copper in 14 karat gold. Right, so it's a little bit more than 0.5% gold. The other, 40% is just other stuff. So is that a pure substance? No, because there's just multiple things present. Yeah, right. So this is a mixture. But what kind of mixture? Homogeneous, yes, because if you, split this ring in half or whatever, you would see it would be fairly uniform within there. So this is a mixture. It would be homogeneous. Would it also be correct to call it a solution? Yes, it would. Okay, so this is why I have a problem with the song when it says pure white gold, because white gold has similar composition to 14 karat gold. Gold is what color? Pure gold. Yellow gold, yeah, it's gold, okay? So white gold, they have to add stuff to it to make it white. So is white gold a pure substance? No, it's a mixture, all right? So you can't technically have pure white gold, right? You have to add something to the gold to make it white. All right, so that's just my tiny qualm. I forget what song it's in. They say pure white gold, and then the chemist in me is like, nah, that's wrong. Okay, that's technically wrong. All right, okay, what about this last one? This is a gold-plated ring. All right, so I have the picture here. It's like a copper ring with gold on the outside. What would we call that? Is it a pure substance or a mixture? Mixture, yeah. All right, let's go a little further. After mixture, heterogeneous, because there's different phases present, meaning like there's a copper solid phase and there's a gold solid phase. So this would be hetero, okay? All right, so let's keep going. All right, these different things. Baking, so a lot of things in your kitchen. So let's go to your kitchen and see, what kind of substances we can't identify. Baking soda, salt, sugar. All right. Let's think, are these pure substances or mixtures? Let's look at baking soda, what we call pure substance or mixture. Pure substance. Why? One formula. Yeah, I made it easy for you. I gave you the formula. All right, so it is a pure substance. Is it an element or a compound? Compound, very good. What about salt? Pure substance. Compound. So it's the same thing. All the first ones in this first row, they're all compounds. Do you agree with me? Because they all have chemical formulas associated with them. They're all pure substances. All right? They all have formulas. Okay, so what if we took salt and sugar and just mixed them together? That would be a mixture. But what kind of mixture? Heterogeneous, because it's two solid phases, all right? Because in theory, if we took those two, the salt and the sugar, and mixed them together in the solid phase, couldn't we also like individually move all of the different particles and like separate them again, all right? Yeah, so here we have a heterogeneous mixture, right? It's non-uniform in composition. All right, what about if we took sugar and salt and dissolved it in hot water? It's a mixture, yes. What kind of mixture? Homogeneous, because when you look at that, is that uniform? Yes, it is. It looks like water. Yes, so this would be a homogeneous solution. All right, very good. So if we think about it, sugar, salt, and water, there are 3 different chemical formulas that I could write to describe what's going on in that sample. Right? Okay, so there we go. Okay, last one. So here is something that you might, run across in your like first aid cabinet. All right, so I have a couple of examples here of rubbing alcohol. Okay, rubbing alcohol is composed of isopropyl alcohol. So here is the chemical formula. This is a pure substance. It's also a compound because there's different elements present all bonded together. You can't, as just people, you can't buy pure isopropyl alcohol. How we purchase isopropyl alcohols in the form of rubbing alcohol. So if you go to Target down the street and want to buy this kind of alcohol, you might get, 70% isopropyl alcohol or 91% isopropyl alcohol, where the majority of it is the alcohol, but the last percent is water. All right, so in 91% isopropyl alcohol, 9% of it is water. All right, and in the 70%, 30% is water. Both of these are homogeneous mixtures, right? Because we have two different compounds that are mixed together, not chemically combined. So basically, the other percent of it would be water in this case. All right. So this is the idea that mixtures can have a variable composition, right? That we can have two pure substances present, but in different ratios. All right. So here's an example. You can have 91% alcohol, or you can have 70% alcohol. They're both mixtures. They're both composed of the same things. All right. Their properties will just be a little bit different within there. All right. So that is the types of matter that we study. All right. So we will come back and use these ideas of, identifying pure substances, mixtures, when we look into the ideas of, physical changes, separations, and things like that. Okay. So let's kind of move on here to the next part of the chapter. I'm going to be kind of talking about these five, or these three different sections kind of all at the same time. We'll look at, properties of matter. We'll look at the difference between kinetic energy and potential energy to chemists, because how physicists do it is a little bit different. And then look at different units of measure and do some calculations with energy. All right, I'll be kind of talking about all of these things at the same time. So property of matter. Now that we know how to distinguish different categories of matter, we can look at their properties. So it's just something that we can measure or observe within our samples. So one of the things that we can look at with a sample is look at its state of matter at room temperature and pressure. So whether something's a solid, liquid, or gas, that would be a property of that substance that you are studying. So the physical state that we see, that we observe of a piece of matter or a sample is based upon two competing factors, kinetic energy and potential energy. Right? So kinetic energy is related to temperature of the sample, right? Also related to how fast the particles in that sample are moving within one another. Potential energy is energy based upon the position of an object. So potential energy is related to the attractive forces of the particles being attracted towards one another. So whether we see something as a solid, liquid, or gas tells us the balance between kinetic energy and potential energy of our sample. When we think about solid, liquid, and gas, which state has, you think, the most kinetic energy? Just use your intuition. Gas, because they're moving the fastest, all right? So in a gas sample, sometimes you can make a gas sample by heating the thing up. All right, if you heat the thing up, you're giving more energy to your sample to go on and move those particles and increase that kinetic energy. When kinetic energy is really, really high, you'll actually overcome attractive forces that come from potential energy. We will come back to this idea in chapter 11, so you just have to be a little bit patient with me. All right, so let me bash on physics for a minute. All right, so if you've taken physics and thought about, kinetic energy, potential energy, all right, I feel like you'll see diagrams like this, where you have conservation of energy, right? You have potential energy, you have a ball, and then you drop the ball. When you hold the ball up here at some height, that ball has high potential energy, but as soon as you drop it, the potential energy converts to kinetic energy until it hits the ground or something. That's physics, I think. All right, that's how I think physics is. Where, you have a bicyclist, they're converting kinetic energy to increase its potential energy. until they're at the top of the hill, and then they can, go down the hill, convert that potential energy back out to kinetic energy. Or, our friend Katniss here, she can take that, that bow and pull the arrow back to change the position of the string, increasing the potential energy. And then once she lets go of that string, that potential energy converted to kinetic energy to send the arrow forward. That's physics. Kinetic energy, energy from movement of matter or of a mass. So, when the arrow is moving, that's high kinetic energy. Based upon the position when her arms are, moved like this, that is high potential energy. So you can see how position is related to potential energy, movement, velocity is related to our kinetic energy. So that's physics. With chemistry, it's a little bit different, all right? It's a little bit different. So in chemistry, here we have 3 different samples: oxygen, solid, oxygen liquid, and oxygen gas. So we see differences in these different samples, okay? So how we differentiate these different samples of oxygen, solid, liquid, and gas based upon their kinetic energy. The kinetic energy of these 3 different samples is based upon the temperature of those samples, right? So if you look really closely at these diagrams, these pictures, you can read the thermometer, right? In the solid sample, the thermometer reads 31 Kelvin. In the liquid sample, it's a little bit higher, 69 Kelvin. But in the gaseous sample, it's a lot higher. It's almost 200 Kelvin, right? So here, I'm trying to convey the difference in kinetic energy of these different samples based upon the temperature of the sample that you can read from the thermometer. What's a little harder to see is the difference in potential energy, right? Potential energy, just like our physics, actually, let me go back to kinetic real quick, because I asked you, when we think of a solid, liquid, gas, which sample has the most kinetic energy? You all said gas real fast, but within our thermometer example here, it's saying the same thing, that our gas sample, it's at the highest temperature, it possesses more kinetic energy than the rest, right, where we have our oxygen gas sample. All right, so if we move on to potential energy, so our potential energy is different in these different samples based upon the states of matter we see, solid, liquid, and gas, and how that packing is arranged. And we talked about this before, that there's a lot more free motion. The particles are not interacting in a gas sample because they're all just bouncing off of one another. So potential energy described by your particle positions from one another or those attractions, all right? So a little tip here, within these 3 different samples, if I wanted to turn oxygen solid to a liquid, this would be a physical change. Because when I turn oxygen solid to a liquid, so it's oxygen solid, oxygen liquid, am I changing the identity of the thing? No, it's still oxygen solid, it's still oxygen liquid, it's still oxygen. Right? So this is a physical change because I'm not changing the identity of the thing. All I'm doing is changing the total energy of the system. All right? And what I do is just change, how far apart particles are away from one another. So converting between any one of these pictures would be a physical change, melting something from a solid to liquid, or boiling something from a liquid to a gas. Those are all physical changes. Okay, so a little bit harder now. All right, we talked about the physics definition, now the chemistry definitions. Still keep in mind, kinetic energy is related to motion of particles. That's still true in chemistry. And potential energy is related to motion, or not motion, but position of particles. That is still true. We just do it a little bit different within chemistry. So with kinetic energy, we still use the same equation that folks use in physics, where kinetic energy of your sample is equal to 1/2 mv squared. All right? So I think this is an equation you get on your examinations, but you need to know how to manipulate the units and the numbers to get to the actual value that, that you want within here. So kinetic energy is measured in joules. That's the SI unit for energy. And so a joule is a kilogram meter squared over second squared. So in order to use this equation properly, so you get joule out, is that you need mass to be in kilograms. You need meters per, or you need velocity when you input it into this equation. You need it to be in meters per second. All right, and so then when you square the velocity, you get the unit of joules, kilogram, meters squared per second squared. So regardless of how the question is worded, you need to make sure that you convert those variables to the appropriate unit before you do plug and chug. So kinetic energy, simple enough. If you've taken physics, it should be a review. What is different and what confuses new chemists like you the most is potential energy. So in chemistry, how we approach potential energy is through Coulombic attractions and repulsions. Right? So the equation for Coulombic attractions is, so the potential energy is equal to Q1 times Q2 over D, which stands for distance. Q1 and Q2 represent charges. D represents the distance between those two charges, all right? So now let me explain. That should make no sense to you. Should make no sense to you, so let me explain. Okay, so if I have a charge, let's say it's a positive charge. I'm gonna call Q1, it's a positive charge. Q2, another charge, is nearby. It is also, let's say it's also a positive charge. All right? So if Q1 and Q2 are both positive and they're separated by some distance, all right, they're separated by some distance. Okay, there we go. If I have two positive charges close to one another, so turn on your monkey brain. If you have two positively charged particles near each other, are they going to be attracted towards one another, or are they going to be repelled by one another? They're going to be repelled by one another, right? Yes. So how we describe this is through this graph. This graph that I'm going to draw right here, this is going to help you a lot in this course in multiple chapters. So if Q1 is positive and Q2 is positive, if we multiply two positive numbers together, what is the sign of the numerator? Positive, yes. Okay, so if the whole numerator is positive, okay, let's see how distance changes that. Okay, let's go back to this example. We have two positive charges near one another. We say that they are repelled from one another. What if we bring those particles closer together? You're gonna feel more repulsion, yes. Yes, so if you think about this equation, if our numerator is a positive number and you bring those two particles closer together, how does D change in this picture? D gets smaller. So potential energy, if our denominator gets smaller, this whole number gets bigger. So what we see here in this graph, this is how I like to draw it, right? Repulsions. This would be something like two positive charges, or it could be two negative charges. It's the same thing, all right? What you see here is if you have two positive charges and you decrease the distance from them, you bring them closer together, that the repulsions between them goes up, all right? So that's what you see right here, that as distance, you bring them closer together, the repulsion that they feel starts to go up. Right, that you need to put energy into the system to keep those two particles really, really close together, right? You have to literally use your muscles to try to put them together. That's what this graph is saying within repulsions. All right, so let's flip it. Let's say that Q1, let's say it's still positive. Q1 is positive. But let's say Q2, the other charge, let's say it's negative. Okay, what does our monkey brain say? They're attracted. They're attracted towards one another. Yes. So as we bring those two attracted particles closer to one another, the attractions should start to feel stronger, right? As the distance decreases between both of them. All right, so let's do the same kind of analysis here. All right, if Q1 is right there, oh, sorry, these are lowercase. I meant to make them capital. So if Q1 is a positive number and Q2 is a negative number, and we multiply those two numbers together, what is the sign of the numerator? Negative. All right, so if this whole value at the top is a negative number and we're dividing by a distance, all right, if we bring those two particles closer and closer, those two attracted particles closer and closer to one another, shouldn't this number get larger? It should get more negative as D decreases in value. And so that's what we see on the bottom half of this potential energy curve. And this is attractions. So we'll see it when we have oppositely charged particles. And what we see here is that potential energy becomes negative. Potential energy becomes low when attracted particles are close together. All right, and so what we see here, D, our x-axis, that the negativeness of this whole potential energy value goes more negative as distance becomes a smaller number. You have a question? Yeah, with chemical bonds, yes, you'll find a well. Yes, we'll talk about more about that in chapter 5. No, that fish just means the fish sign. No, it just means proportional to. With kinetic energy and potential energy, this whole slide, we will calculate kinetic energy like a number. We will never